A single stone can hold 4 billion years of Earth's story. We are about to explore 24 rock faces that recorded the evolution of planetary time, and by the end, you will be able to read the history of our world written in stone. These are not just cliffs and canyons, they are archives. They hold evidence of cosmic collisions, the breath of the first oxygen, and the rise and fall of entire species. How did a global freeze get locked inside striped iron? And what catastrophic flood carved a landscape in just days? These silent stone sentinels have been keeping a diary of everything. What do you believe is the most important lesson the Earth's deep past can teach us about our future? Deep within the remote wilderness of northwestern Canada, a battered outcrop of gray and pink rock holds the title of the oldest known piece of our planet. This is the Acasta Gneiss, a 4.03 billion-year-old witness to Earth's violent infancy. To stand before it is to look upon the very foundations of the continental crust, a time when the world was still cooling from a global ocean of magma. The intricate bands and swirls visible in its face are not just patterns, they are a textural record of immense heat and pressure, a story of how this rock was tortured and transformed deep within a young, unstable planet. It represents the first solid skin of the world, the primordial nuclei around which all future continents would slowly gather. Scientists determine its incredible age through a process called isotopic dating, which measures the steady radioactive decay of elements like uranium trapped inside its zircon crystals, acting as a radiometric clock that started ticking billions of years ago. This ancient sentinel is not alone. On the coast of Greenland, the Isua Greenstone Belt, at 3.8 billion years old, tells a complementary story. Within its twisted, rust-colored layers, geologists have found chemical signatures of liquid water and hints of what might be the earliest evidence of life, a potential whisper of microbial activity in a newly formed world. These rocks are more than just old. They are a bridge connecting the violent geology of a newborn planet to the delicate chemistry that may have sparked biology itself. What does the profound resilience of these stones, surviving unimaginable eons of change, tell us about our own place in deep time? They are the first chapter in a diary that spans billions of years, a diary whose next entries were written not on land, but in the endless dark of the ancient deep. But that new world of rock and water was about to undergo a transformation so profound it would set the stage for all future life. 2.5 billion years ago, in what is now the vast, rust-red landscape of Australia's Hamersley Basin, a quiet revolution began in the ancient oceans. The rock faces here, known as banded iron formations, tell this story not with fossils, but with breathtaking stripes of deep red and metallic gray. Each perfectly defined layer is a page in a planetary diary, recording the single most important atmospheric change in Earth's history, the Great Oxidation event. These spectacular stripes formed on the seafloor as trillions of microscopic cyanobacteria, for the very first time, began to harness the power of sunlight to create energy, releasing oxygen as a waste product. This microbial innovation was a catastrophe for the ancient world. The free oxygen immediately bonded with the immense amounts of dissolved iron in the seawater, causing it to precipitate out in thick, rusted layers on the ocean floor. Season after season, year after year, this process repeated, laying down a rhythmic record of chemical change. The presence of these rocks across the globe, from the Sokoman Formation in Canada to the iron-rich ranges around Lake Superior, proves this was not a local event. It was a planetary-scale transformation, a literal rusting of the oceans that forever changed the chemistry of the air we now breathe. This oxygen, initially a toxic pollutant to most ancient life, eventually became the foundation for complex organisms, including us. These very same banded iron formations are also our planet's most important source of iron ore, meaning the very steel in our buildings and cars is forged from the remains of that ancient, oxygen-starved ocean. How incredible is it that a simple biological process invented by microbes could rewrite the entire planetary script, setting into motion a chain of events that would eventually lead to a world teeming with life. This biological breakthrough, locked in stone, was just the beginning of a much longer story written in flesh and bone. High in the Canadian Rockies, a slab of dark shale holds one of the most important pages in life's diary. The Burgess Shale is a 508-million-year-old rock face that freezes a single moment from the Cambrian explosion, a period of unbelievable evolutionary creativity. While other fossils might show only shells or bones, the Burgess Shale is different. It preserved the complete soft-bodied animals, the squishy and the delicate creatures that usually vanish without a trace. This unique fossilization happened through a perfect storm of conditions. These animals lived on the edge of a steep underwater cliff. Occasional mudslides would sweep them down into deep, oxygen-poor water, where scavengers could not live and decay was incredibly slow. The mud gently compressed them, capturing their exquisite details in fine clay before they could rot away. The result is a spectacular menagerie of early life. There is Anomalocaris, a nightmarish predator with compound eyes and grasping claws that was likely the apex hunter of its time. There is Opabinia, a bizarre creature with 5 eyes and a trunk-like claw. And there is Hallucigenia, so strange that scientists initially could not tell which end was its head or its back. This is not just a collection of curiosities. It is a detailed record of early animal body plans, a showcase of morphological innovation where nature was experimenting with the very blueprints for life. The predator-prey dynamics visible here, with the first complex eyes and defensive spines, show an evolutionary arms race that would shape ecosystems forever. Similar sites, like the Chengjiang fossil beds in China, confirm this explosion of diversity was a global phenomenon. Some of these Chinese fossils are so perfectly preserved that they have revealed the earliest evidence of neural tissue, offering clues about how the brain and nervous system first evolved. So what sparked this sudden diversification? The causes are still debated, a combination of rising oxygen levels, genetic toolkits becoming available, and the evolutionary pressure of being seen or eaten for the very first time. The legacy of this explosion is all around us in every animal phylum that exists today. This incredible archive of life, however, was just one way the planet kept a record. The very same stone that preserved these delicate creatures would also capture moments of unimaginable violence, etching the story of planetary catastrophe into the cliffs. But that evolutionary burst was almost erased by a force from beyond our world. Etched into the ancient landscapes of South Africa is the Vredefort Dome, the deepest and largest scar from a cosmic impact our planet has ever endured. 2 billion years ago, an asteroid perhaps 15 kilometers wide slammed into the Earth with an energy beyond comprehension. The rock face here does not tell a gentle story. It is a record of pure violence containing shocked quartz, a mineral whose crystal structure was instantly deformed by the immense pressure, and tektites, globs of rock that were melted and thrown into the atmosphere only to rain back down as glass. The impact was so powerful it is believed to have cracked the continental crust, potentially triggering volcanic eruptions on the opposite side of the globe and altering the planet's climate for millennia. This is not an isolated event. In the Yucatan Peninsula of Mexico, the buried Chicxulub crater tells a similar, more recent story. The layer of iridium-rich clay found in rocks around the world points directly to this 180-million-year-old impact, the cataclysm that ended the age of the dinosaurs and cleared the stage for mammals to rise. Identifying these ancient crime scenes requires detective work. Geologists look for those telltale signs, the shocked minerals, the shatter cones radiating through the bedrock, and the unique geochemical fingerprints of extraterrestrial material. Yet from this utter destruction comes creation. The Sudbury Basin in Canada is the eroded remnant of a 1.85 billion-year-old impact. The colossal heat from that event melted the crust, concentrating valuable metals like nickel, copper, and platinum group elements into massive deposits. What was once a scene of apocalyptic violence is now one of the world's most important mining districts, providing the critical materials for our modern technology. How do these cosmic collisions, written in shattered stone, remind us of our planet's vulnerability and its profound interconnectedness with the dynamic solar system? They are a stark lesson that our world's history is shaped by both the life teeming on its surface and the chaos raining down from the heavens, a chaos that also forged the very resources we depend on. This focus on external forces leads us directly to the immense power churning within the planet itself. Massive outpourings of lava have repeatedly reshaped the planet's climate and its destiny. In western India, the Deccan traps stand as a monumental testament to this power, a staggering series of rock faces built from countless layers of basalt lava that once flooded the landscape. This is not the story of a single volcano, but of a catastrophic plumbing failure in the Earth itself. Around 66 million years ago, a colossal mantle plume, a superheated upwelling from deep within the planet, punched through the crust, unleashing millions of cubic kilometers of molten rock over tens of thousands of years. The rock record here is a stark timeline of fury, one lava flow piled upon another, each layer freezing a moment of this planetary scale eruption. The timing is chillingly precise, as this paroxysm of volcanism occurred simultaneously with the asteroid impact that ended the Cretaceous period. The environmental consequences were apocalyptic. Beyond the lava itself, which would have incinerated everything in its path, the volcanoes pumped unimaginable quantities of sulfur dioxide and carbon dioxide into the atmosphere. This would have first triggered a volcanic winter, blocking sunlight and collapsing food chains, followed by an intense period of global warming as the carbon dioxide lingered. This 1-2 punch of impact winter and volcanic greenhouse would have created an utterly hostile world, pushing countless species, including the non-avian dinosaurs, beyond the brink of survival. The Deccan traps are not unique. The Siberian traps in Russia tell an even older and perhaps more devastating story. 252 million years ago, a similar event there is linked to the Permian-Triassic extinction, the single greatest loss of life in Earth's history, nicknamed the Great Dying. Even the more recent Columbia River basalt group in the northwestern United States, though smaller in scale, shows how these repeated eruptions can fundamentally alter a continent's landscape and atmosphere over millennia. So what drives these fiery outbursts from the planet's interior, and how do they shape life's trajectory? These immense rock faces are the direct result of the Earth's restless inner engine, a reminder that the ground beneath our feet is not always solid, and that the planet's most transformative forces often rise from its deepest, hottest depths. This story of climate-altering cataclysm, written in layers of cooled lava, finds its counterpoint in a completely different kind of rock face, one that tells the story of a planet not burning but freezing solid. The Earth's fiery interior gave way to an entirely different kind of force, one of immense and silent cold. Across the vast expanse of the Canadian Shield, the ancient bedrock is not smooth and pristine. It is scarred, scratched, and polished to a high sheen, as if a giant hand had taken a piece of sandpaper to the continent. These are glacial striations, the unmistakable signatures of ice ages past. For millions of years, colossal sheets of ice, sometimes over 2 miles thick, advanced and retreated across the landscape. They did not simply cover the land, they sculpted it. At their base, these glaciers were like slow-moving rivers of abrasive grit, dragging countless rocks and boulders that carved deep, parallel grooves into the solid granite below. These grooves are a compass frozen in time, pointing in the exact direction the glacier was flowing. Scattered across these same landscapes are erratic boulders, massive stones that sit completely out of place, deposited far from their original bedrock source by the relentless power of the ice. These are not random features. They are the data points glaciologists used to reconstruct the behavior of ancient ice sheets. By mapping the direction of striations and the paths of erratics, scientists can trace the flow and retreat of glaciers over millennia. The story gets even more detailed with landforms like moraines, the piles of rocky debris pushed along and dumped at a glacier's edge, marking where the ice paused for centuries. Or drumlins, those elegant teardrop-shaped hills that formed under the ice itself, indicating the precise direction of its flow. This is not just ancient history. The same processes that carved the iconic U-shaped valley of Yosemite, so different from a river's V-shaped cut, are still at work today in Greenland and Antarctica. By understanding how these icy giants moved and melted in the past, recorded so clearly in the rock, we can create more accurate models to predict their behavior in our warming world. How will the immense ice sheets of today respond, and what will their retreat mean for global sea levels? The rock faces scratched by ice provide a critical manual, a guidebook written in stone for the changes we are now witnessing. This frozen record, however, is just one chapter in a much larger story written by the planet's most dominant feature, its oceans. Rising from the sea like a monumental page from a global diary, the iconic white cliffs of Dover are not made of stone in the ordinary sense. They are a breathtaking accumulation of countless trillions of microscopic plankton called coccolithophores. These tiny algae, each no larger than a speck of dust, lived in the warm, sunlit surface waters of a Cretaceous ocean 100 million years ago. When they died, their intricate calcium carbonate skeletons, resembling minuscule hubcaps, drifted slowly down to the seafloor, building up layer upon gentle layer over millions of years. This soft ooze eventually compressed into the brilliant white chalk we see today, a direct physical record of a vanished marine world. This process is how all limestone forms, a rock type that acts as the planet's ultimate marine archive. From the vast platforms of the Bahamas to the dramatic peaks of the Italian Apennines, these carbonate rocks are libraries of past oceanic conditions. By analyzing the chemical isotopes locked within these calcium-rich shells, scientists can read the ancient sea's vital signs. The ratio of oxygen isotopes reveals the water temperature when the organism grew, while carbon isotopes tell a story of biological productivity and the health of the entire food web. The beautiful Scaglia Rossa limestone of Italy, with its striking pink and red hues from iron oxide, is particularly famous. Its layers are packed with specific microfossils that act like barcodes, allowing geologists to precisely date the rock and correlate these layers with identical ones across the globe, creating a unified timeline for Earth's history. But these archives hold a deeper lesson about planetary cycles. Limestone is the Earth's primary storage vault for carbon, a crucial regulator of our climate. The constant formation and subduction of these rocks over eons have helped balance the amount of carbon dioxide in the atmosphere, maintaining a stable environment for life. What profound secrets of ancient ocean chemistry and climate stability are we yet to decode from these calcium-rich layers, and how does their slow, rhythmic formation mirror the rapid, human-driven changes we see in our modern seas? This journey through the deep oceanic past, written in limestone, now brings us to the immense forces that lifted these seafloor archives toward the sky, to the tectonic dramas that built the very mountains around us. These crumpled and fractured rock faces are the Earth's ultimate record of continental collision. In the Swiss Alps, the sheer scale of the deformation is breathtaking. Entire mountainsides are bent into impossible waves of stone, with layers of rock that were once horizontal now standing vertically or folded into tight, intricate loops. These dramatic structures began forming 65 million years ago, when the African tectonic plate slowly and relentlessly pushed northward into the Eurasian plate. The immense force of this collision did not simply push the land upward. It caused the Earth's crust to buckle, break, and slide over itself in massive sheets known as thrust faults. Structural geologists act as detectives at this rocky crime scene. By meticulously mapping the folds and faults, they can reconstruct the direction and magnitude of the ancient forces at work. They study how different types of rock respond to stress, with some layers bending plastically into folds while more brittle rocks shatter into faults. This process is not just about creating spectacular scenery. As these layers of sedimentary rock were folded and buried deep within the growing mountain belt, the increasing heat and pressure cooked the organic material trapped within them, transforming ancient marine life into the hydrocarbons that become oil and natural gas, trapping them in reservoirs within the arched folds of anticlines. This story of mountain building is a repeating cycle. The worn-down, rolling hills of the Appalachian Mountains in the eastern United States tell a very similar tale, though from a much older collision. Their gently folded strata are the deeply eroded roots of a mountain chain that was once as grand and towering as the Alps, forged hundreds of millions of years ago during the assembly of the supercontinent Pangaea. How do these crumpled layers reflect the relentless forces driving Earth's surface evolution? They are a direct physical manifestation of the planet's dynamic interior, a slow-motion ballet of colliding continents that shapes and reshapes the world over hundreds of millions of years. This narrative of tectonic force, written in folded stone, finds its quiet counterpart in the delicate impressions left by life itself. Massive dunes once rolled across a landscape of utter dryness, their forms now frozen solid into the very walls of Zion Canyon. The Navajo sandstone is a breathtaking archive of an ancient desert, a sea of sand that covered the American Southwest 200 million years ago during the Jurassic period. Its most striking feature is the sweeping, curved lines that cut across the cliff faces in elegant arcs. These are not mere patterns, they are cross-beds, the preserved remains of the very slopes of monumental sand dunes that migrated across this vast emptiness. Each curve is a snapshot of the wind itself, a record of its direction and power as it pushed these towering mountains of sand grain by grain. Sedimentologists decipher this story by reading the geometry of these layers. The angle of the slopes tells them about the size of the dunes, while the direction the curves face reveals the prevailing wind patterns of a lost world. This was an environment of extremes, a place where water was a distant memory and life was a constant struggle. In the similar Coconino sandstone of the Grand Canyon, the story of that struggle is written not in bones but in footprints. Perfectly preserved trackways show where ancient reptiles scrambled up the steep faces of dunes, leaving behind a poignant record of their daily journey across a harsh and unforgiving landscape. These sandy archives are not unique to North America. Modern deserts like the Sahara or the Namib show us this very process in action, with dunes marching across the land in the same way, building the same internal structures that, given enough time and pressure, will one day become solid rock. So what does this testament to endurance, written in stone, teach us about resilience? It shows that life, even under the most arid and demanding conditions, finds a way to persist and leave its mark. The very rock that speaks of such profound dryness also holds the key to understanding its opposite, a world of steamy, oxygen-rich swamps that would one day power our modern civilization. Deep within the black seams of Appalachian coal, an entire world lies compressed. These rock faces are not stone, but energy, the preserved remains of vast swamp forests that thrived 300 million years ago during the Carboniferous period. The atmosphere then was thick with oxygen, a legacy of the towering tree ferns, giant club mosses, and horsetails that covered the land. When these plants died, they did not fully decay in the stagnant, waterlogged swamps. Instead, they accumulated into thick layers of peat. Over millions of years, the immense pressure and heat from overlying sediments cooked this peat, slowly driving out water and volatile gases, and concentrating the carbon into the dense, black rock we know as coal. This process, repeated across the globe, created the vast coal reserves that would later fuel the Industrial Revolution and power our modern world. But these coal beds are more than just fuel. They are a detailed botanical record. Paleobotanists study the intricate impressions of leaves, bark, and spores preserved in the shale layers above and below the coal, piecing together the evolution of the very first forests. The fossils found here are breathtaking. At the Joggins Fossil Cliffs in Nova Scotia, the entire ecosystem is frozen in time. Erosion has revealed upright fossil trees, their hollow trunks serving as traps that captured the earliest reptiles and amphibians, preserving them in perfect detail. This includes the tiny, lizard-like Dendropeton, offering a direct look at the first vertebrates to truly conquer the land. The high oxygen levels of this period, fueled by these global forests, allowed for gigantism in invertebrates, leading to predators like Meganora, a dragonfly with a wingspan nearly the size of a hawk. So how did these ancient, oxygen-producing forests ultimately create the carbon-rich rock that now, when burned, alters our modern atmosphere? They were the planet's greatest act of carbon sequestration, pulling enormous amounts of carbon dioxide from the air and burying it deep underground for millions of years. We are now in a geological instant, releasing that stored carbon back into the sky, reversing a 300 million year process in a mere few centuries. This profound legacy, written in layers of compressed sunlight and life, connects the deepest past to our most pressing present. Our own era is now being written into the rock record, a stark new chapter defined by human activity. Geologists call this proposed new time the Anthropocene epoch, and its markers are not fossils or minerals, but the unmistakable signatures of our modern civilization. In urban quarries and coastal cliffs, we are depositing layers that will baffle future scientists. These include microplastics, tiny synthetic particles that now weave through sedimentary layers worldwide, and spherical fly ash particles from the relentless burning of fossil fuels. Perhaps the most telling marker of all are the radionuclides, the radioactive elements like plutonium that were scattered across the globe by nuclear weapons testing in the 1950s and 60s. These artificial isotopes create a sharp, global spike in the sedimentary record, a precise timestamp of humanity's newfound power to alter the planet's very chemistry. To see this new layer being formed, scientists look to places like Crawford Lake in Canada. The deep, still waters of this lake create perfectly preserved, thin layers of sediment at its bottom. Within these delicate bands, researchers can see a clear, undeniable transition. One layer shows the arrival of industrial ash from nearby factories. The very next layer captures the radioactive fallout from those first atomic tests. This is not a slow geological change. It is a sudden, violent inflection point recorded in mud and stone. The debate now is whether this human signal is significant and permanent enough to define a new geological epoch. Will these materials fossilize? Will a layer of compressed plastic bottles one day form a new type of rock, a plastiglomerate that tells the story of our disposable culture? What will a future geologist, 1,000,000 years from now, deduce about our society from these strange, artificial layers? They will read a story of rapid technological advancement, but also one of profound global pollution, a time when one species briefly became the dominant force shaping the planet's geological future. This indelible human signature, pressed into the strata, shows that our legacy is now inseparable from the Earth's deep time story, a story that continues to unfold in natural laboratories across the globe. The silent stories within rock faces remain timeless until we learn to read their calendars. Deciphering the age of these planetary diaries is a feat of scientific detective work, relying on two powerful methods that complement each other. Relative dating acts like putting events in order without knowing the exact dates. By studying the layered cliffs of the Grand Canyon, geologists apply the simple principle of superposition, which states that in an undisturbed sequence, the oldest rocks are at the bottom and the youngest are at the top. This is combined with fossil succession, the idea that distinctive fossils appear and disappear in a specific, reliable order through the rock layers. Finding a particular fossil, like a trilobite or an ammonite, in a rock layer instantly tells a geologist its relative age compared to layers containing different fossils. But to assign a number, an absolute age in millions of years, requires a different tool, one that acts as a clock ticking at a known, steady rate. This is radiometric dating. It measures the natural radioactive decay of unstable isotopes within minerals. For the most ancient rocks, like the Acasta Gneiss, scientists turn to uranium lead dating, which analyzes the slow, predictable decay of uranium into lead within incredibly durable zircon crystals. These zircons are time capsules, surviving billions of years of geologic turmoil while preserving their internal atomic clock. For younger volcanic rocks, like the massive Fish Canyon tuff in Colorado, the argon-argon method is used. It measures the decay of potassium into argon and has been crucial for precisely calibrating the global geological timescale, pinning down the dates of mass extinctions and other key events. The Earth itself provides another clock through its magnetic field, which has reversed its polarity numerous times throughout history. These magnetic reversals are recorded like barcodes in the iron-rich minerals of cooling lava flows, creating a global pattern that can be matched and dated from one continent to another. These techniques do not work in isolation. They form a web of cross-validating evidence. A date from a volcanic ash layer using argon-argon methods can confirm the age of a fossil found in that same layer, which then helps date all the other sedimentary layers above and below it through biostratigraphy. How does cracking these temporal codes transform our understanding? It turns a static collection of rocks into a dynamic, unfolding narrative, allowing us to place the violent impact at Vredefort before the quiet accumulation of the Burgess Shale, and to see the great oxidation event as a prelude to the age of coal. This precise chronological toolkit allows us to truly appreciate how each unique rock face, from the youngest volcanic island to the oldest continental craton, contributes its own irreplaceable verse to the epic poem of planetary time. Tiny filaments etched into a 3.465-billion-year-old Australian rock may be the oldest known signatures of life. The apex chert in Western Australia presents a profound and controversial puzzle for geobiologists. Within its fine-grained, silica-rich layers, scientists have identified microscopic structures that resemble the shapes of modern cyanobacteria. These are not fossils in the traditional sense, with preserved organic material, but rather intricate casts and molds, the empty spaces where cells once were, filled in and exquisitely preserved by the mineral quartz. The argument for their biological origin rests on their complex, branching, and segmented forms, which appear too ordered and consistent to be the result of random mineral growth. The debate surrounding these structures is fierce, a necessary scientific rigor applied to a claim of such monumental importance. Skeptics have proposed that these shapes could be artifacts of the rock's complex geological history, perhaps formed by the twisting and shearing of minerals under intense heat and pressure, creating lifelike illusions in the stone. To test this, researchers use the most advanced tools available, from high-powered electron microscopes to laser Raman spectroscopy, which analyzes the chemical residues within these microscopic tubes for the faintest organic signatures that might remain. This search for life's dawn is a global pursuit. In the Nuvvuagittuq Greenstone Belt in Canada, similar claims have been made for even older, 4.28-billion-year-old hematite tubes, pushing the potential origins of life back into the hellish, water-rich environment of the Hadean Eon, not long after the Earth's crust first solidified. If these most ancient claims are true, they suggest life emerged with astonishing speed, a spark that caught almost as soon as the planet was cool enough to allow it. How do these minuscule impressions, smaller than a grain of sand, challenge everything we assume about life's beginnings? They force us to consider that life may not be a rare cosmic accident, but a fundamental and persistent outcome of planetary chemistry, an inevitable process given the right ingredients and enough time. This evidence of primordial life, written in the most durable pages of silica, sets the stage for the next great leap in complexity, a biological revolution that would eventually transform the entire planet. A dramatic ridge of sandstone just outside Denver, Colorado, holds the footprints of giants. Dinosaur Ridge is a Mesozoic time capsule, its tilted rock faces exposing a stunning array of tracks and bones from 150 million years ago, a period when behemoths like the long-necked Apatosaurus and the formidable predator Allosaurus ruled this land. This is not a static display. The tracks, preserved in what was once the muddy shoreline of a vast inland sea, are frozen moments of behavior. Paleontologists analyze these trackways like a detective at a crime scene. The spacing between prints reveals the animal's speed and gait. A set of deep, heavy impressions might show a massive sauropod lumbering slowly, while a series of sharp, widely spaced three-toed prints tells the of a theropod dinosaur on the hunt, its movement swift and purposeful. Sometimes the tracks even show a limp or the drag of a tail, offering an intimate glimpse into the daily life and struggles of these ancient creatures. But the bones tell a different, deeper story. The Morrison Formation, the geological layer exposed here, is one of the world's richest dinosaur graveyards. The formation of these bone beds is a story of catastrophe and preservation. Herds of dinosaurs likely perished together during regional droughts, their bodies concentrated around dwindling water sources before being rapidly buried by river sediments or even volcanic ash, which protected them from scavengers and sealed them for eternity. It is this volcanic ash that provides the critical key to dating these deposits. The minerals within the ash, like zircon crystals, contain radioactive clocks that allow geologists to pin this entire ecosystem to a precise moment in the late Jurassic. This story of dinosaur dominance was a global one, On the other side of the world, the flaming cliffs of Mongolia's Gobi Desert present a completely different Cretaceous world. Here, the rock faces blaze red under the sun, preserving not the giants of North America, but a unique desert ecosystem filled with smaller, often bizarre dinosaurs like the parrot-beaked Protoceratops and the infamous egg thief Oviraptor, a dinosaur once wrongly accused of stealing other creatures' eggs, now known to have been brooding its own nest. What do these majestic remnants, from the colossal to the cunning, say about evolution's successes and its catastrophes? They show a world of incredible diversity and adaptation, a reign that lasted for over 150 million years, only to be abruptly ended by forces beyond their control. Their legacy, stamped into the stone, is one of both triumph and fragility, a reminder that even the most dominant species are not immune to planetary upheaval. The very rock that entombed these giants would soon cradle the small, scrappy survivors of that catastrophe, the mammals who would eventually inherit the Earth. Deep within a German quarry, a dark, oily shale holds a moment of perfect stillness from 47 million years ago. The Messel Pit is a window into a lost world, a tropical ecosystem that thrived just 16 million years after the dinosaurs vanished. This is not a collection of bones, but a preservation of life itself. The rock faces here are so detailed they capture the iridescent shimmer on a beetle's wing, the delicate outline of a bat's wing membrane, and even the last meal in a prehistoric fish's stomach. This miraculous preservation is the result of a deep, volcanic lake whose oxygen-starved bottom waters prevented decay and scavengers from disturbing the remains. Animals that fell into its depths were entombed in fine, bacteria-inhibiting mud, their forms captured down to the smallest detail before being slowly transformed into the oil shale we see today. This site is a cornerstone for understanding the mammalian radiation that followed the dinosaurs' demise. Here we find Darwinius massili, a lemur-like primate that provides critical clues to our own evolutionary branch. We see the earliest ancestors of the modern horse, Propaliotherium, a dog-sized creature that browsed on leaves in the lush forests, its skeleton so complete we can study its every bone. The sheer diversity is staggering, from giant ants and crocodiles to over 1,000 species of plants, painting a comprehensive picture of a greenhouse world, a climate optimum far warmer than our own. Scientists use these fossils to trace evolutionary lineages with unprecedented clarity. The stomach contents of a fossilized crocodile reveal its final fish supper, while pollen grains preserved on a fossil bee tell us exactly which flowers it was pollinating. This level of detail transforms abstract concepts of evolution into tangible, observable evidence. How does this exquisite time capsule illuminate life's resilience after catastrophe? It shows a planet bursting with new opportunities, where mammals rapidly diversified to fill the ecological voids left by the giants, setting the stage for the world we know today. This snapshot of a steamy, vibrant Eocene paradise stands in stark contrast to rock faces that recorded a very different kind of change, not in life, but in the very ice that once gripped the continents. A jagged line in the Scottish cliffs shattered humanity's perception of time. At Sycamore Point, the rock face does not tell a single story, but two, separated by an abyss of missing years. Below, gray slabs of Silurian sandstone stand vertically, like the pages of a book turned on its edge, twisted and hardened by immense mountain-building forces 430 million years ago. Above them, lying in perfectly peaceful, horizontal layers, is a younger cap of Devonian red sandstone, deposited a staggering 65 million years later. This dramatic meeting, this angular unconformity, is where modern geology was born, When the 18th century naturalist James Hutton stood here, he saw not a chaotic jumble but a profound truth. The vertical rocks below had been formed, then folded upward by unimaginable force, then worn down to a flat plain by the slow, patient work of wind and rain over millions of years. Only then was the area submerged again, allowing the horizontal layers above to be deposited on this eroded surface. This single cliff face provided the physical evidence for deep time, proving that the Earth's history was not measured in thousands of years, but in hundreds of millions. It was a cycle of creation and destruction, endlessly repeating. Hutton's revelation here dismantled the dominant theory of catastrophism, which held that all geological features were formed by sudden, biblical-scale disasters. Instead, he proposed uniformitarianism, the radical idea that the same gradual processes we see today, like erosion and sedimentation, sculpted the planet over vast eons. The principle is elegantly simple: the present is the key to the past. Sycamore Point is not unique in this lesson. The Grand Canyon is a masterclass in unconformities, with multiple gaps in time visible between its many layers, each representing millions of years of history erased by erosion. Every unconformity is a missing chapter in the Planetary diary, a silent testament to time so deep it defies easy comprehension. How did one man's observation of this rocky discordance fundamentally rewrite our place in the universe? It gave us the conceptual framework to read the Earth's long story, a story that includes not only slow cycles, but also moments of breathtaking, catastrophic speed. The landscape of eastern Washington state looks like it was torn apart by giants. This is the channeled Scablands, a vast, scarred terrain where the very rock face seems to have been violently peeled back. Etched into its bare basalt plains are features so immense they defy belief: giant ripple marks standing 15 meters high and stretching half a kilometer apart. These are not the gentle ripples of a stream bed. They are the permanent signatures of a catastrophic flood of unimaginable scale, a deluge that reshaped the land in a matter of days. For decades, geologist J. Harlan Bretz battled a skeptical scientific community to prove these formations were not carved by slow glaciers, but by a sudden, colossal outburst of water. His evidence was written in the stone in the form of massive dry waterfalls and deeply gouged channels called coulees. The story these rock faces tell is one of climatic drama. 15,000 years ago, a towering ice dam in present-day Montana held back a vast inland sea, Glacial Lake Missoula. When that dam suddenly ruptured, it unleashed a wall of water hundreds of meters high, rushing across the landscape at speeds exceeding 100 kilometers per hour. The force was so powerful it plucked entire basalt columns from the ground and carved intricate potholes into the solid bedrock. Geomorphologists have since calculated the flood's staggering volume, estimating its flow was 10 times the combined discharge of all the rivers in the world today. This was not a single event, but a cycle of rupture and refill that happened dozens of times, each megaflood adding another layer of scarring to the land. The significance of this discovery was a paradigm shift, proving that geology is not always a story of gradual change, but can be punctuated by moments of breathtaking, catastrophic violence. This terrestrial evidence even provided a key analog for planetary scientists, who see similar gigantic flow channels on the surface of Mars, suggesting our neighboring planet also experienced its own ancient watery cataclysms. What do these violent water scars, frozen in stone, reveal about the sudden impacts of a shifting climate? They are a stark warning of the immense power locked within our planet's ice, and a demonstration of how quickly stable systems can collapse, unleashing transformative forces that rewrite the very ground beneath our feet. This narrative of swift, powerful change finds its counterpoint in the patient, persistent work of a much slower sculptor. Rising from the central Australian desert like a colossal, rust-red heart, Uluru stands as a profound testament to deep time, both geological and cultural. This is not merely a rock, it is an Inselberg, an island mountain, and a sacred archive for the Anangu people, who have been its custodians for tens of thousands of years. Its geological story begins over 550 million years ago, when this entire region was the bottom of a deep sea. The sand and mud that would become Uluru were eroded from ancient mountains to the south, carried by powerful rivers, and deposited in vast alluvial fans. Immense pressure from subsequent tectonic collisions compressed these sediments into Arco sandstone, a coarse-grained rock rich in feldspar that gives Uluru its distinctive rusted hue. The entire formation was then tilted almost 90 degrees, lifting these once horizontal layers vertically towards the sky. Millions of years of erosion then stripped away the surrounding softer rock, leaving this monolithic icon standing alone in the vast plains. The weathering patterns on its surface are a language of their own. The dramatic parallel fluting down its sides are water scars, etched by rare but torrential downpours over millennia. The numerous caves and overhangs are not random features, but were carved by chemical weathering and wind, creating shelters that have been used for ceremony and daily life for countless generations. The nearby Kata Tijuta, also known as the Olgas, shares this incredible genesis but is composed of a different rock type, conglomerate, offering a fascinating comparative view of how the same tectonic forces can produce dramatically different forms. For the Anangu, every fissure, cave, and stain on the rock's surface is part of a living cultural landscape, a tease or dreaming story that connects the people to the land and to their ancestors. Each feature embodies a creation event or a moral lesson, from the activities of the ancestral Mala people to the journeys of the Uluru, the poisonous snake. This creates a powerful duality. A geologist sees the folded strata and reads a history of titanic continental shifts. An Anangu elder looks upon the same folds and sees the physical evidence of a creator being's actions. How do such formations bridge scientific and cultural understandings of time and place? They demonstrate that a single rock face can hold multiple, equally valid truths, a narrative of physical forces intertwined with a continuous human story of reverence and belonging. This fusion of meaning, written in sandstone, shows us that the planet's diary is not just a record of chemistry and physics, but also of spirit. The very minerals that give Uluru its color also hold a more precise record of the ancient environments from which they came, a climatic signature locked in atomic bonds. The very minerals that give Uluru its color also hold a more precise record of the ancient environments from which they came, a climatic signature locked in atomic bonds. Deep within a Nevada cave called Devil's Hole, a single, massive rock face of pure calcite tells a story not of grand collisions or ancient life, but of subtle, rhythmic changes in the planet's climate. This is the world of stable isotopes, where geologists act as chemical detectives, reading the Earth's past temperature from atomic variations too small to see. The key lies in the ratio of different oxygen atoms, or isotopes, trapped within the calcite's crystalline structure. When rainwater falls, a slightly heavier oxygen isotope, oxygen 18, is more likely to condense and fall from a cloud than the lighter, more common oxygen 16. During ice ages, when vast glaciers lock up this lighter oxygen, the world's oceans become enriched with the heavier oxygen 18. Organisms that build their shells from ocean water, or minerals like calcite that precipitate from groundwater, incorporate this telltale ratio. A higher proportion of oxygen-18 in the Devil's Hole calcite directly corresponds to a colder, glacial period, while a lower proportion signals a warmer interglacial world like our own. This creates an incredibly detailed, layered climate record stretching back hundreds of thousands of years, its rhythmic bands of isotopic variation matching perfectly with the data pulled from ancient ice cores in Greenland and Antarctica. This powerful technique turns seemingly inert rock faces into precise planetary thermometers. Stalagmites and stalactites in caves across the world, known as speleothems, grow in the same way, their layers providing high-resolution climate diaries for continents that lack ice sheets. But like any instrument, these proxies have limitations. Scientists must meticulously calibrate them, ensuring the isotopic signal reflects only temperature and is not skewed by other local factors like rainfall source or evaporation rates. The immense value of this data is its application to our future. By analyzing how the climate system responded to past changes in greenhouse gases, whether slowly over orbital cycles or rapidly from volcanic eruptions, we can refine our models and improve predictions for planetary responses to current warming. How do these microscopic atomic signatures, etched into stone, help us foresee the behavior of vast ice sheets and ocean currents? They provide the critical long-term context, showing us the full range of the Earth's natural climate variability and precisely where our human-driven changes now exceed it. This same chemical detective work, reading the subtle language of rocks, is also the key to finding the resources that power our modern world. The quest for precious metals often begins with reading the subtle language of ancient riverbeds, now turned to stone. The Witwatersrand Basin in South Africa is the ultimate testament to this, a rock face that has yielded over 40% of all the gold ever mined by humanity. Its story begins over 2 billion years ago, in a time before multicellular life, when powerful rivers flowed across a vast plain. These rivers carried not just sand and mud, but also incredibly dense particles of gold eroded from distant mountains. In the slower-moving bends and gravel bars of these ancient waterways, the heavy gold settled out, mixing with other dense minerals to form rich, pebble-strewn layers known as conglomerates. Over incomprehensible eons, these river sediments were buried, compressed, and cemented into rock, preserving those gold-rich layers as a treasure map written in stone. Geologists call these placer deposits, and they form through the simple, relentless force of gravity and water sorting Earth's materials. But not all riches are found in old rivers. Often, the most valuable minerals are born from fire and pressure deep within the Earth's crust. Hydrothermal veins are a completely different kind of deposit, formed when superheated water, rich with dissolved metals, forces its way up through cracks and fissures in the bedrock. As this mineral-laden fluid cools and its pressure drops, the metals it carried can no longer stay dissolved. They crystallize out, filling the fractures with veins of quartz, silver, copper, or gold, like filling the cracks in a broken vase with precious mortar. The geological cycles that create these concentrations are slow and specific, requiring the perfect combination of heat, fluid, and a pathway to the surface. Sometimes, however, the catalyst is not gradual but catastrophic. The Sudbury Basin in Canada, which we encountered as an ancient impact crater, is one of the world's most productive mining districts for nickel and platinum. The unimaginable energy of the asteroid impact melted a vast portion of the crust and underlying mantle, creating a deep magma chamber rich in metals. As this molten rock slowly cooled over thousands of years, the heavy metals sank to the bottom of the chamber, forming a gigantic, concentrated ore body. This proves that from utter planetary destruction can spring immense geological wealth. So how does learning to read these rocky ledges guide us toward a future of sustainable resource extraction? It teaches us that these deposits are not random, but the result of specific, understandable events. By deciphering the formation processes, we can prospect more intelligently, minimizing the environmental footprint of exploration. We learn that these are finite resources, the product of unique planetary moments that cannot be repeated. This knowledge pushes us to use what we find with greater efficiency and to recycle with more urgency, ensuring the wealth of the Earth sustains us for generations to come. A drone hovers silently before the sheer face of El Capitan, its laser scanner painting the granite with invisible light. This is the new frontier of geological discovery, where cutting-edge technology is giving us the power to read rock faces without ever touching them. Light detection and ranging, or LiDAR, creates exquisitely detailed three-dimensional maps by measuring the time it takes for millions of laser pulses to bounce back from the rock surface. This data builds a digital twin of the cliff, a model so precise it can reveal fractures thinner than a hair and track the subtlest signs of erosion over time. Combined with high-resolution drone photography, these tools allow geologists to study the most dangerous and inaccessible formations from the safety of a lab, preserving delicate sites from the wear and tear of human boots and hands. The applications are profound. In hazard assessment, these models can identify unstable rock slabs that threaten communities, allowing for early warnings and mitigation. In education, students can now put on a virtual reality headset and stand atop a Himalayan peak or descend into the Grand Canyon, conducting virtual fieldwork that was once logistically impossible. Beyond our planet, satellite-based spectroscopy is used to analyze the light reflected from Martian cliffs, identifying mineral compositions from orbit and guiding rovers to the most scientifically interesting sites. How will these non-invasive eyes deepen our decoding of planetary time? They allow us to ask new questions of old stone, to see patterns and connections across vast scales that were once invisible, merging the patient wisdom of geology with the instantaneous power of the digital age. This high-tech horizon does not distance us from the natural world but draws us closer, transforming our appreciation for how these ancient rock faces inspire not just scientific inquiry, but also art, philosophy, and a deeper connection to the epic story of our planet. A rock face is never just a rock face to an artist. For Georgia O'Keeffe, the stratified cliffs of New Mexico were not geological records but symphonies of color and form, their textures and shadows inspiring canvases that translated deep time into visual emotion. This artistic impulse is ancient and universal. High above the plains of Thessaly in Greece, the breathtaking pinnacles of Meteora are not merely sandstone towers. For centuries, they have been a divine canvas, their sheer faces hosting monasteries that seem to grow directly from the stone, a physical manifestation of the human quest for permanence amidst an ever-changing world. Philosophers, too, have looked upon these formations and seen profound metaphors. The iconic face of Half Dome in Yosemite, with its sheer granite wall, has been described as a monument to resilience, its slow, patient exfoliation a perfect allegory for the gradual, often imperceptible process of personal and societal change. This interdisciplinary dialogue between Earth and art enriches our understanding, reminding us that the planet's diary can be read not only for scientific data but for spiritual and aesthetic meaning. This creative conversation is itself etched into the stone at places like Petra in Jordan, where the magnificent rose-red cliffs are not just a backdrop. The Nabateans carved their entire city, including intricate temples and tombs, directly into the living rock, blending human history so completely with geology that one cannot be separated from the other. Their petroglyphs tell stories of people and gods, superimposed upon a narrative of sedimentation and erosion that is millions of years older. Even the act of preservation becomes an art form, as seen in the ancient Chinese tradition of scholars' rocks. These naturally sculpted stones, prized for their abstract forms that suggested mountains, caves, or entire landscapes, were contemplated as art objects, their wrinkles and hollows seen as a physical expression of nature's creative force. So what do these countless artistic interpretations add to our scientific understanding of time's passage? They provide the emotional and cultural context, transforming cold chronology into a shared human experience. They remind us that our own story is interwoven with the planet's, and that our awe, our reverence, and our creativity are all part of the legacy recorded in these 24 rock faces, solidifying their role as the ultimate narrators of Earth's epic story. Each of these 24 rock faces, from the ancient Acasta Gneiss to the modern layers of the Anthropocene, is a unique verse in a single, epic poem of planetary evolution. They are not isolated monuments but interconnected chapters, each revealing a different process in the grand saga of Earth. The banded iron formations tell us how biology first learned to manipulate the atmosphere, a story that finds its echo in the coal beds, where that same atmospheric oxygen fueled vast forests whose buried remains now power our civilization. The violent impacts recorded at Vredefort and Sudbury show how chaos from space can forge the very metals we depend on, while the patient folding of the Alps demonstrates the slow, relentless forces that build mountains and trap the resources within them. The delicate fossils of the Burgess Shale and Messel pit capture life's creative explosions, while the unconformity at Sycar Point and the scars of the channeled scablands bookend these narratives with evidence of both deep time and sudden catastrophe. Together, they form a collective memory, a biography of a living, breathing, and constantly changing planet. This interconnected record provides crucial context for our greatest global challenges. Understanding the ancient carbon cycle locked in limestone and coal is fundamental to addressing modern climate change. The isotopic thermometers in cave calcite and ice cores give us a baseline for Earth's natural climate variability, showing just how far our current trajectory deviates from the norm. The formation processes of ore deposits, from placer gold to hydrothermal veins, guide us toward more sustainable resource management, reminding us that these are finite legacies of unique planetary events. How does this deep time perspective guide our stewardship? It teaches resilience, showing that life has endured unimaginable upheavals, but it also underscores our profound responsibility. For the first time, a single species is consciously altering the same planetary systems, the atmosphere, the oceans, the very surface, that these rocks have silently recorded for billions of years. We are no longer just readers of this story. We have become its authors, writing a new chapter with every action we take. The final lesson these stone sentinels offer is not just about the past, but about our future. From the ancient whispers of the Acasta Gneiss to the stark warnings in the Anthropocene layers, each formation teaches a dual truth of incredible planetary resilience and profound fragility. Life has endured global freezes and fiery impacts, yet its course has been dramatically altered by sudden shifts in atmosphere and climate. We are now the authors of such a shift, writing our own chapter into the rock record at a breathtaking pace. This deep time perspective is not a reason for despair, but a call to thoughtful action, a reminder that we are part of a 4 billion year story and have a responsibility to its next pages. I encourage you to go out and connect with this history yourself. Visit these sites, whether in person or through the incredible documentaries available, and feel the weight of time they represent. Look at a canyon wall or a roadside cliff and see if you can read its story. and I would love to hear which of these 24 rock faces fascinated you the most. Share your thoughts in the comments below. If you enjoyed this journey through planetary time, please like this video, subscribe to the channel, and hit the bell so you do not miss our next exploration into Earth's deepest mysteries. Until next time, keep looking down. The ground beneath your feet has stories to tell if you only know how to